Speaking of service to the industry, our final speaker in the plenary session this morning is Dr. Ron Sinton. Ron is the president and senior scientist at Sinton Instruments, based in Boulder, Colorado. With a PhD in applied physics from Stanford, Ron took his experience in developing highly efficient silicon solar cells and founded Sinton Instruments with the objective of building state-of-the-art testing and measurement instruments for solar silicon cells. These instruments have formed the basis for the solar industry. And so Ron's going to talk us through how this works, and his talk is titled Advanced Characterization of Silicon Solar Cells at IV Test, Now and the Future. Thank you, Ron.
This is my burglar alarm at my business, and it goes right through, whether you have it silenced or not. So 37 years ago, I was a graduate student at Stanford University, and I was working on very high-efficiency solar cells. This is shown here. They were really small. They were on 1 centimeter square die, and I show it next to a modern solar cell. And then I zoom in a little bit so you can start to see that the actual device was only 3 by 5 millimeters. And then I zoom in a little more. You can almost start to see something there. Because what we were doing is using the best available integrated circuit silicon at the time and the best available integrated circuit process in any university anywhere. It was a backside point contact design, 2-micron design rules. We were using photolithography, and we could get 28% efficiency at 120 suns. Now, some people in solar cells thought we were cheating, but it was fine. When you started to look at how these solar cells worked, it was silicon then and now. Some things never change. And what really mattered was the recombination. And so the chart on the left is the percent recombination by mechanism versus incident power density on the horizontal axis. And at the design point, which was 360 suns, our nemesis was Auger recombination. And second in line was emitter recombination. And third in line was bulk recombination. And if you didn't have nearly a perfect bulk recombination, these devices wouldn't even work. And over on the right, you can see that at 100 suns, you could actually achieve 28% with these devices. So this discussion of recombination is totally modern and will be a big part of this talk here. But what would have shocked the 28-year-old version of myself is that you could have nearly perfect silicon solar cells by the billions made in mass production at 24 to 25%. And this is the incredible advance in technology and especially in manufacturing. And this is just shocking. I don't think any of us would have anticipated this even 15 years ago. But there was another development that I'll talk about some today, which came from Australia, and I wouldn't have anticipated this either, and that's PL imaging and EL imaging, which came from Torsten Trubka and Rob Bartos, 2006. And this is an amazing characterization tool that we didn't have and we didn't anticipate. So going on to how solar cells are designed today, this is an APSRC roadmap, which is one of the road mapping organizations, and it shows recombination current on the vertical axis and year on the horizontal axis. And you can still see that the game is to reduce recombination as the metric to improve your solar cell efficiency. And I added some labels here. And the center lines are mostly the front J-naught coming down with year in the projections and the bulk recombination in the middle. The bottom line is the back passivation from TopCon cells, which is a leading contender for the high efficiency cells these days. And I also added the light blue box in the bottom, and that's the Auger recombination, still there. And it depends on the substrate doping, so there's a range. But you can see that we're actually approaching, with these technological recombination sources, down to the fundamental recombination in the silicon. So I'm talking about IV test here today. And the IV test toolkit is basically to measure intensity, sunlight intensity or artificial light intensity as a function of time, voltage as a function of time, and current as a function of time. And when you do this, you get the IV curve shown in blue here, and the sun's VOC curve, which is the outer bound limit of what you can do with this particular solar cell because it doesn't have the series resistance. We also measure the transient capacitance measurement to determine the charge in the solar cell. And the reason we do this is to determine the doping. Because once you know the doping, you can add a third curve here, which is in black, and that's the Auger limit for this solar cell, based on the short circuit current that you've measured, but it also depends on doping and thickness. So you want to measure doping. In this talk, I'm going to discuss measured parameters and interpreted parameters. The measured parameters are kind of whatever you can measure with a voltmeter. You can measure voltage, you can measure current, power, reverse breakdown voltage, things like that. But the interpreted parameters are the ones that you really want to know that influence your cell design, the kinds of things that we saw in the APSRC roadmap. You want to know the capacitance, the series resistance broken down into its components, shunt resistance, bulk lifetime, surface recombination, and doping. And these are trickier to get because you take your voltage data and you have to be much more creative about taking enough voltage data, voltage and current, and feed it into models and in order to interpret them as the right parameter. To emphasize this, I borrowed a slide from Dan McDonald that he presented at the NREL workshop a year ago. And these are Quokka simulations. And down at the bottom in the right, we have the cell efficiency. And then you have 12 different losses that bring you up to kind of a maximum efficiency. And of course, the computer is omniscient. It knows everything. So we have 12 different losses here that it's enumerated. And I've kind of labeled them here as recombination losses and series resistance losses. And 4% relative of them are recombination losses. 3% are series resistance losses. Now, you would like your IV tester to report these 12 parameters. I'm sorry to tell you that this is not possible, but what I'll talk about is what is possible to get the best measurements you can so that an experimentalist with targeted experiments might be able to separate these out as best as possible. So we'll go back to these 3 IV curves that I've shown here, but I'll show them in a different view. I'll zoom in right on the maximum power point and show them as power on the vertical axis versus voltage. And we've got the IV curve, the sun's VOC curve, which is the IV curve without series resistance, and we've got this Auger limit. Now, we can take the sun's VOC curve and put it into a model to interpret it as lifetime versus carrier density. And I'll do that on the right here. using the laser. And when you do that, you've got carrier density on the horizontal axis and 1 over tau on the vertical axis. And this is the interpretation that you use to get the surface recombination, the emitter saturation current density, which is from the slope of this curve. And so from that, you can go back to the left and add a 4th curve onto the our collection of curves, and that's the Auger recombination with the emitter recombination. And now you know almost everything except the bulk recombination. But if you know the Auger, the emitter, and the total, then the bulk is just the difference. And so we're starting to get to know an awful lot about this little solar cell we're measuring here. So if you do a loss analysis, going from the maximum power point on the red curve, which is the sun's VOC curve, and start reducing recombination, you go up towards short circuit current as you have much more, less and less recombination. This is shown on the left. We have the efficiency on the vertical axis versus the total J naught from both bulk, emitter, and Auger. And it's just a line going up monotonically to the left as you reduce your J naught. And you can get into the Auger limit, which I've shown again as the little blue box. And it's different for heavily doped substrates and lightly doped substrates. So that's a choice you can make. But rather than, you notice that the vertical line doesn't go to the maximum power point on the Auger limit curve. And so I find this kind of analysis to be limiting. And this is what Quokka was doing. And it doesn't get you to the absolute limit. So I'll do something else here. I'll look at the increase in efficiency as you go up the gradient that passes through the maximum power points as you reduce the recombination here. And it's approximately 96% of JSC, and that makes the math really easy. So, of course, I'll do that. And what you get is the blue curve here. And you can see that it's super linear, and it increases incredibly once you get below 10 femtoamps per centimeter square of total J naught. And I want you to kind of keep that number in mind, 10 femtoamps. There's incredible increases in the efficiency once you get below 10 femtoamps for later in this talk. And so I think this is an important concept here, that some of the energy loss analyses, whatever, don't take into account that as you reduce the recombination, you actually move up to higher voltage maximum power points. And I found this in not just the Quokka analysis, but others that are very similar. So if you take this all together, I've got the pi on the right, and that's the power that you would get out at the Auger limit. And then we can see that there's about 6% bulk recombination, 1% J naught recombination, and 3% series resistance recombination. So you know what to work on, and you know what the best you could possibly get to in this way. Now, how does this work in practice? This is a dashboard on a measurement instrument, and if you're measuring with time, and we've sped this up a little bit, you can see that the total recombination in gray is about 10%, and we can see series resistance in purple at about 3%. And I'll move on to a clean version of this here. And so for this population of cells, you can see that the total recombination actually has 2 peaks. And this leads to 2 or 3 peaks in the efficiency distribution as well, once you get up to thousands of cells. And I'll remove total recombination so we can see behind it. And what we see here is that the design of the cell has a very low J naught, and it has a low power loss around 5%, but that there's a second peak, which is over at 10%. And so we have something to work on. We can see here that there's a process control or a technology problem in the surface recombination. So I'm going to go back to this concept of measured and interpreted parameters here and look at the interplay between bulk lifetime J naught doping and thickness. And this just came up in the last few weeks. And we are a test and measurement company. And so a lot of our little research projects are because of customer technical support. So sometimes you come in on a Monday morning and someone somewhere will be asking, how accurate is the lifetime and J naught measurement? And as I mentioned before, when you get below 10 femtoamps per centimeter square, you get a rapid increase in the efficiency, and that's where people are now. That's 2 orders of magnitude lower in the emitter saturation current density than we were just 5 or 10 years ago. So the instrument can stay the same, but the capabilities that people expect from it to be useful are always changing. And so what we found in this case was the limiting factor in the precision of the measurement is the wafer input specifications as purchased. And so we did a little experiment, and the input resistivity is usually very wide on a wafer specification. And that's because as you grow the ingot, you have dopant segregation and the resistivity changes. And so we have a box profile there on the left from 0.5 to 1.5 centimeters, and that's just a random distribution of the box profile. And for wafer thickness, you have plus or minus 15 microns typically. So we've shown that as a Gaussian on the right. So if you pick a nominal value, a nominal midpoint value for these, and specify it in your interpretation of data, but in actual fact, your wafers have this kind of distribution, then when you run it through the analysis, you get this kind of result. And so we have lifetime on the vertical axis and carrier density, and on the left, and you can see that there's a factor of 3 in difference that you can get in the lifetime. And the emitter saturation current density is the slope of the line in the linear region of the right-hand graph. And you can see that it even changes sign. So it's non-physical what you can get within the reasonable variation of wafer thicknesses. So there's a good clue about what's going on here if you just fix the doping and leave the wafer variation in there, and it tightens up tremendously. And to go farther, we actually measure the doping each time. So if you use the measured doping, it magically cleans up and is very useful data. And we can see on the right, we're measuring a J naught of 10 femtoamps plus or minus 10%, which is about 1 femtoamp. So the key thing here is that input specifications are determining the precision of the tool. And the other thing, I said it was magic. Actually, what's going on here is that when we measure the doping, we have to use a very wide distribution of carrier density data and frequency data in the time domain. And just putting more data into the model gives a more precise result. So going forward into the future, we've got a nice IV tester, but it's almost impossible to measure the cells that we're getting. And the reason for this is that silver is expensive, and so people have removed silver from the cells at the stage where you want to measure them. And this shows, huge bus bars in the early 2000s, no bus bars now. What this means practically is that if you have 16 bus bars, the super multi-bus bar cell, they call them, you have all these probe bars and you can almost not see the cell anymore. And in production, sometimes they use just half the bus bars and then a fudge factor to report the real efficiency. So we're working on a project where we do very minimalist probing, and we use PL imaging to get a lot of the information. So the concept here is that we get the sun's VOC data because it doesn't need much probing. We get image data, and then we use those to construct the IV curve and the sun's VOC curve. And this is a little animation where you do the line scan PL and the sun's VOC, and then you bin your cell magically. It looks something like this, or from the other view, something like this. And the result is that you get almost all the data you got from the probed IV tool, but you also get the image-based analysis. And we saw several papers on Tuesday, in the first day of this conference, of image-based analysis from UNSW, and they have a long history, and so we can build on these tools. So this is what it looks like in production at a line speed of 1 per second. You can see the IV curves dancing around and the PL images on the right. And then we'll go to a lifetime view, and you can see that these are very individual wafers. They all have different lifetime and J0 characteristics, and then the power loss analysis. So we did validate this method, and we used a set of 4 types of cells going from HJT to TopCon with 0 bus bars. And we benchmarked it against our conventional tester. And so with respect to sun's VOC data, it's very, very good, as might be expected, because you don't pull current. Here we have the new tool on the vertical axis versus the conventional cell tester on the horizontal axis, and it's nicely proportional. And we have the same thing for resistance on the right, and this is much more difficult, of course, because this factor of 2 in resistance is only plus or minus 6 millivolts or so. One thing that we didn't anticipate is that when you're benchmarking against the existing tool, what we found is that the existing tool is starting to fail for these super multi-bus bar cells. And so the uncertainty horizontally with the conventional cell tester is much bigger than the uncertainty on the new tester. And this is a reproducibility metric that I'm talking about here. So it's not just a matter of matching the conventional tool. The conventional tool is starting to fail. With respect to series resistance, we can compare to 10 years of data in the literature. And our data is the black data. First thing we see is that series resistance is very tight these days in the black data versus what it was 10 years ago, and that we're getting comparable results. And so here's kind of a grand finale, which is the 4 sets of solar cells compared the conventional cell tester on the horizontal axis and the new tester vertically. So we've kind of shown that you can be as good as a standard tester, but could it be better? And certainly it can, because now we're using the image data. And so I'm going to show a few slides here, and we're showing efficiency, vertical axis versus estimated bulk lifetime on the horizontal axis for 4 different kinds of solar cells. But we'll focus on the 16 bus bar top con cells, and we're showing efficiency versus estimated bulk lifetime. And for cells that we classify as good, we can see that the efficiency is in the high end of the distribution, and it has a dependence on bulk lifetime of about half an absolute percent when you go from 1 millisecond to 10 milliseconds. Then we have cells that we're classifying as dark, and we see that the efficiency is independent of the bulk lifetime, and it's in the low end. But when we complement this with the electronic data, we find that these are the high J0 cells. So these are the ones that have a process control problem. And then finally, we've got an image classification of oxygen rings, and we can see that those are the low lifetime cells with the strong dependence on bulk lifetime. Finally, we saw that in the Quokka model, we had the series resistance in 6 different components. Well, we can get 2. We can get the grid resistance and kind of a contact plus spreading resistance. That's the best we can do, and this shows our correlation with grid resistance. So this brings me into the end, and I wanted to acknowledge all the Australian collaborators over the years, and this has been since 1985, and this is a partial list, and just in general, the vibrant Australian community that's had such an impact on this field. So the conclusion is our strategy is to measure everything at IV test. The conventional probed IV is almost impossible for the new cells, but solutions exist, and they're looking very promising. Thank you very much.
Thank you so much, Ryan. We're almost at time that we could take 1 or 2 quick questions. Vanandi?
Thanks for the great talk, Ron. So with so many people adopting zero bus bar, is it almost getting to a point where your cell current measurements of cell current and fill factor become difficult, because you can actually make a cell with very little metal now, and you can make assumptions about how that cell is going to be interconnected in a module. Right? Then you can't compare that cell if you're doing a multi-bus bar cell, where you actually have to have solder pads there for all the interconnection. So how do you compare cell 1 and cell 2?
So you do have to take the geometry into account. With a line scan PL, you can get the series resistance components of the grid, and then once you know the geometry of how many bus bars there will be in the module, you can calculate what this cell resistance will be once it's strong. And so from the image, you can get enough information about series resistance to know how it will behave in a module once it's wired up.
But there are different methods of zero bus bar. Some are using adhesives that might have some effect on the current, module current. Others are using solving, and others are using films. So they're all using different methods.
Right. So what we're characterizing is the cell as it exists at this point in the process, which is what has always been done. There's always a cell to module loss that's later. But to have this data here and then have the module data, at least you know what damage you've done in the middle. Yeah.
Okay, thank you. I think I might have to leave it there. Let's thank Ron one more time for your.
Okay.